Alright, this is Algebra 2, Chapter 5, Section 5. Theorems about roots and polynomial equations. Okay, so this one's going to be a little tricky. We have something called the rational root theorem. And the rational root theorem really works really well with cube functions in the standard form. And it says that if we have a situation where we have a very polynomial in standard form, then we can get potential roots by getting factors of things. So, for example, I'll use the actual numbers here that they give us. We have 21x squared plus 29x plus 10. All right. So this guy here is the coefficient for the leading highest degree variable. And then this guy is the constant back here. And the first thing that we do is we get all the factors of both of those things, the leading degree variable and the constant. The constant has factors of plus or minus 1, plus or minus 2, plus or minus 5. These are all numbers that it can be multiplied or divided by. And plus or minus 10. Well, this guy has factors of plus or minus 1, plus or minus 3, plus or minus 7, and plus or minus 21. And what happens is that in order to find what the potential, these are the potential factors of the roots. In order to find what the potential root is, we would have to get a ratio, a fraction of the factors of, we'll call this guy, of the leading coefficient. So the book calls it P over the, of the constant over the leading coefficient. So you're basically going to get iterations of this. There's tons of combinations. Let's start with this 1. It'll be 1 positive over 1, which equals 1 positive, and then it would be negative. So 1 over 1, negative 1 over positive 1, negative 1 over negative 1. See where I'm getting with this? 1 over negative 1. So there's many iterations of it, but we just say plus or minus 1 because that's all what that means. And then there's 1 over the 3 plus or minus 1 over 3. 1 over the 7 plus or minus 1 over 7 plus or minus 1 over 21. That's just the ones. Then we go into twos. This can get really long. Plus or minus 2 over 1, so which is just 2, plus or minus 2 over 3, plus or minus 2 over 7, plus or minus 2 over 21. And then with the 5s in the numerator, and with the 1s, and then the 10 in the numerator, and so on and so forth. So these are all versions of what the roots could be. One of those could be the roots. One of those two can be the roots. So with that in mind, since I know it's a square, I know it has two roots, you would actually sort of guess and check. You would plug all of these guys in to find out how many roots we're dealing with. And the book says eventually you'll find that it's x plus 2/3 times x plus 5/7. That means that the roots were negative 2/3, and negative 5/7. So it sort of narrows down our choices. You're asking yourself, well, why can't you just, factor this and find it that way? My answer to you would be, that's what you usually do. When it's a degree of 2, when it's a polynomial at a degree of 2, but what if you get degrees higher? Then this actually becomes really, really helpful. And it's actually really, really helpful when you do degrees of 3. So we're going to do one. We have a 3x cubed plus 7x squared plus 6x minus 8 equals 0. Again, we have two factors here. We have factors in front of the 3 and the factors of the 8. So for the 8, it'll be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. For the leading coefficient, it'll be plus or minus 1, plus or minus 3. Which does help things. It limits our guys. So plus or minus 1 over plus or minus 1 is plus or minus 1. 1 over 3 plus or minus 1/3. 2 over 1 plus or minus 2. 2 over 3 plus or minus 2/3. 4 over 1 plus or minus 4. 4 over 3 plus or minus 4 over 3. Plus or minus 8 plus or minus 8 over 3. So it's going to be one. They want you to find the rational roots. And what you're going to have to do is you're going to have to plug it in. This is either 1 or 0. That's just one root here. Yeah, there's just one root. You have to plug all of these guys in. You got to plug these guys into the original equation, and eventually you'll get an answer. Well, that's going to take forever to guess and check, so I already took the liberty of doing it for you. And the number that seems to fit is 2/3. So you would plug it into here. 7 times 2/3 squared plus 6 times 2/3 minus 8 equals 0. So that seems to fit. Once you plug it in, you'll get 24 over 7 plus 28 over 9 plus 4 minus 8. And you'll find that all of that will equal 0, so it checks. So this is, since this is a, 2/3, then your root would be 2/3. So you get all the combinations thereof. You'll plug these guys in one at a time, positive and negative. So not just one, but 1 and negative 1, 1 and negative 1/3, and you plug them all in, and eventually you'll find that 2/3 will work out of all of them. So there's only one root in this particular problem, and that root is at 2/3. And then we get another problem where they want you to not only find the roots, but also factor and try to find the factor of it by naming all the roots. So here's how this works. They want us to find the roots of 2x cubed plus x squared minus 7x minus 6. What are those roots? All right, well, what you can do is first we're going to get those factors of u and those factors of u. So for this guy, it's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. With this guy, it's plus or minus 1, plus or minus 2. And then we're going to, you can get all those iterations thereof. So, you know, plus or minus 1, plus or minus 1 over 2, plus or minus 2 over plus or minus 2 over 2, which is plus or minus 1, and then plus or minus 3 over plus or minus 3 over 2, plus or minus 6, plus or minus 6 over 2, which is plus or minus 3. So these are all the, so there's 1, 2, 3, 4, 5, 6 times 2, so there's 12 potential, potential roots, and one of them has to fit. So we plug it in, plug it in, plug it in, and we find out eventually that 2 works. We find out that 2 works. So this was step 1 here. Now this is step 2. Actually, I'll do it in a different color. Find out the one that works. So we plug them in, plug them in, plug them in, and we notice that 2 works. 2x 2 cubed plus x, plus 2 squared minus 7 times 2 minus 6 equals 0. And it does. This works. And then after we do that, then step 3, to find the other potential roots, what they may be. Since we found 2, we're going to do long division. We're going to do long division. So we're going to divide is it 2? Yeah, 2 should work. 8 times 2 is 16, plus 4 is 20, minus 14, which is 6. 6 minus 6 is 0, so it does work. So if the factor is 2, that means that the polynomial is x minus 2. And we're going to divide that into not long division, synthetic division, since we're doing a bilinear equation, but divide it into 2x cubed plus x squared minus 7x minus 6. So you can do either long division or you can do synthetic division. It would be easier to do synthetic division. So this would be 2. This would be 2. 1, negative 7, negative 6. Drop to 2. This would be 4. 4 plus 1 is 5. Times 2, 10. 10 take away 7 is 3. 3 is 6. Negative 6, 6 is 0. So then this equation would be 2x squared. Actually, let's put it over here. 2x squared plus 5x plus 3. Once you get to this step here, oh my god, that's not what I selected at all. You have your potential one here. This is 2x squared plus 5x plus 3. You can do the diamond method and find out what those two guys are. I'm not going to do that. You guys know how to do that. And you'll get 2x plus 3 times x plus 1. So then your roots are 2, negative 3, negative 1. 3 halves, negative 1. And if you're wondering about the 3 halves, this would be 2x plus 3 equals 0. Subtract these from both sides. 2x equals negative 3 divided by 2. X equals negative 3 halves. So that's where that comes from. Okay. So that's that. It's a long process, I will not lie to you. And there's a lot of ways to get lost in there. Speaking of ways to get lost, conjugate root theorem. And what the conjugate root theorem says is that if we have irrational roots, then its conjugate is also a root. So when you have complex roots, if you, let's say you have 2 plus root 6i, then as a root, then you also have another root of 2 minus 6i, which is its conjugate. Okay? You have two roots here. Every complex root has a conjugate root associated with it, in addition to just regular rational numbers. That is x plus b. Alright. They have a problem here where they say we have this equation and it has roots 1 plus I one minus I, and then here we have square root of 2. So all these guys have conjugates, rational and irrational. So if there is a root 2 root, it also has a conjugate of negative root 2. If we have an imaginary 1 minus I, it also has another root of 1 plus I. Each rational, irrational root, an imaginary root, has a conjugate, has a twin. And the twin is always opposite of its sign. So opposite sign, opposite sign, opposite sign, opposite sign. Okay. So with that information in mind, they give us a scenario here. Where they give me a root of 8, 2, 8, 2, 2 minus 3i. They want to know what the other root is and then write the actual equation. So when we write the actual equation, these two guys are kind of easy to figure out. This would be x minus 2 times x minus 8, because those are the roots. That's what those guys look like when I multiply these out. Here we have this 2 minus 3i. So in the same form of x minus u, let's call it u. Let's say this guy equals u. And then its conjugate would be x minus negative u, right? The conjugate in this case would be 2 plus 3i. Those guys are the conjugate. So we're now sub it back in. It's going to be x minus 2 minus 3i times x minus 2 plus 3i. Alright, that's the first step, setting it up. Step 2, you gotta multiply these guys out. Let's start with the conjugates first. So x minus 2 minus 3i times x minus 2 plus 3i. Doing the math out, you get x squared minus 2x plus 3xi minus 2 minus x minus plus 4 minus 6i minus 3xi. Wait, I've done this bad boy. 4 minus 6i 3xi plus 6i minus 9i squared. Remember, I squared means negative 1. So this goes, this goes. This would be plus 6i. That was my mistake. This goes, and these stay. So this is x squared minus 4x. Here's a 4. And remember, this is the same thing as saying negative 10 or plus 9. So plus 13. Alright, the next step is I'm going to multiply this times x minus 8. So this would be my step 3. And that gives me x cubed minus 4x squared plus 13x minus 8x squared plus 32x minus 104. Which turns into x squared cubed minus 12x squared plus 45x minus 104, and then we multiply that times x minus 2. And then that would be my step 3, 4. So then that gives me x to the 4th minus 12x cubed plus 69x squared minus 194x whoops, skipping steps, plus 45x squared minus 104 x minus 2x cubed plus 24x squared minus 90x plus 208. And then combining all that together, I get x to the 4 minus 14x cubed plus 69x squared minus 194x plus 208. Okay. We were given 3 of the 4 roots. 1, 2, 3. We used a conjugate to find the 4th root. I multiplied the conjugates out, then I multiplied it by the other 2 to get this guy. This is the quartic function or quadratic polynomial that has those roots. Okay. All right, last one. Descartes' signs. Let polynomial be a real coefficient written in standard form. He noticed, and this is not always the case, but he noticed that if I have some root, let's use the example that they give us here, x to the third minus x squared plus 1 equals 0. He noticed that when they switch from sign to sign, so here's a positive, right? I'm going to put a positive in front. Consecutive sign to sign. So we have a positive to a negative from here. So this is from positive to negative at this point. And then from here to here, it's going to be a negative to a positive. He noticed that when you have that scenario, and this is a positive scenario, so that tells him that it's have 1 root, 2 root. So he noticed that this can have a potential of 2 roots or 2 minus 2 roots, which is 0. So I can either have 2 roots or no roots that are positive. This is when it's positive. So this is of p of x. He also noticed that if he switches the sign and say, okay, let's call this p of negative x. So this would be negative x cubed minus negative x squared plus 1 we now get negative x cubed plus x squared plus 1. There's no switch signs here. From here we go from negative to positive. So this tells me I have 1 real root. If I subtract 1 minus 2, meaning every even number, I get a negative number. So that doesn't count. There's no such thing as negative number of roots. So I either have 1 negative root, I will have 1 negative root, or I'll have 2 positive or 0 positive roots. And you have to graph it to confirm. And when we talk about negative root, is where it crosses the x axis. So this particular graph crosses here and has a negative root, does not have a positive root. So 2 or 0, so it's 0 roots and positive, and then 1 negative root. That's what it does. Count the number of signs, and then you should be able to find out how many roots it has and where it's on which side of the graph. So for this guy, 2x to the 4, this is for positive x, minus x cubed plus 3x squared minus 1 equals 0. Here I got positive to negative. Here I got negative to positive. I'll just right here. I have 1. I have negative to positive, so I have 2. And I have positive to negative, so I have 3. So I can have either, for positive roots, I can have either 3 or 3 minus 2, which is 1. So I can have either 3 or 1 positive roots. When I do negative x, so it'll be 2 negative x to the 4th minus negative x cubed plus 3 negative x squared minus 1. This is going to be positive 2x to the 4. This is going to be negative times a negative, which is positive x cubed. This is going to be positive times a positive, so 3x squared minus 1. So I only have one change here. So for negative roots, I only have one. So I should have one negative or one positive or 3. So we can always check the graph. And looky, I have one positive root and one negative root. Positive root, negative root. So the graph confirms that I have one positive and one negative root. Neat little trick. The last question says, can you confirm real and complex roots by graphing? No. We can't graph complex numbers per se in a rational realm. We can only graph real numbers, rational numbers. Okay, that is our section. Hope you have a great rest of your day.